Test, test. Morning, folks. How y'all doing? Got a good weekend, I hope? Yeah? Good weekend? Busy. Okay. Always busy. All right, listen, I have a couple things to point out to you. First of all, if you look on the website, I put that reading quiz on there. So if you go to the website, which is linked from Moodle, I think almost everybody has been to this site, right? More or less? All right, so if you go there, you look at the old quizzes and exams, I've put places for the quizzes that we'll have. We're going to have more than 4, but you can find the quiz there, and then the answers are there as well. Okay? So you can take a look at that if you like. On some of the tests in the past, I've had a video, but I'm not going to do that for these. I think the answers are fairly simple, so I don't need to have an explanation. But if you find that you really like that, you can just let me know. I'll make them. Valerie? The tests are going to be very similar, yeah. Right. And the test will largely come from the book, except for we had that section that prior to when we got into the book on units and the SI system and all that business. So that will also be on the test next Thursday. All right. Yeah. Oh no, I'm not sure. DJ? I'm not sure. I'll let y'all know next Tuesday, and I'm not sure of the length or how long you're going to have. I mean, I expect we'll just take the whole class period, but I'll just have to. I'll let you know on Tuesday. Never done this before. I know that y'all haven't. I haven't either. Okay. That test will cover all of Chapter 1, obviously, which we're going to finish up soon, and then we'll do a portion of Chapter 2. All right. I'm planning perhaps to do a quiz on Tuesday. Oh no, but that's really great for you because then you get a little extra practice on chapter 2 because the quizzes they're not totally inconsequential, but they're fairly inconsequential. So that'll give you some practice and prepare for the exam because the exam will also include not all of chapter 2, but a portion of chapter 2. But just stay tuned to that. If you have your book, go and start reading chapter 2 and start preparing for a quiz on a portion of chapter 2 next Tuesday. But that's still a little bit tentative. I'll let y'all know on Thursday. All right? How do y'all feel about a quiz on? Yeah. No, it's really good for you because it'll force you to read. And I know that most of you will just put, yes, good. Most of you will put off until when to study for the exam? Wednesday night, yeah. So this will make you study at least a Monday night, right? And Wednesday night. Okay. Let's see, we left off last time on synovial joints, and I think we did some clicker questions last time as well, and we'll do that again today. Just ask you a couple questions so you can get your clickers out. And you can use your notes or anything of that. This is a lever. I have my pivot point right there. I have a load right here, and in order to support that load, I have to apply a force right here. Which type of lever is this? Is this a type 1, type 2, or type 3 lever? Oh, yeah, you can talk to people, but please click on the answer. All right, I'll stop at 30 seconds. Just guess if you don't know. Remember, you do get credit for these, even if you get the answer wrong. Excellent. Gosh, we should just cancel class because you're all so great, right? Now, you're paying lots of money to be here, so let's your money's worth. All right, so let's say, since you're on such a roll, let's just do one more. What is this lever? This is my force, A, B, or C, 1, 2, or 3. What type of lever is that? And remember, Fazal / the author of the book said that it's, what is it? Scissors, wheelbarrow, tweezers, right? Which one is this? All right, I'll stop at 32 seconds. Again, if you haven't yet. Excellent. Yeah, I got that down. We'll look at some different types of levers in the human body today as well. Let's say that I have a seesaw. It is balanced in the middle part, just like all seesaws are. Let's say that we have a 100-Newton person, that's a little person, at a distance of 2 meters, and at a distance of 1 meter, I have a 50-Newton person. That's even a little bittier person. All right. Is this in rotational equilibrium? Is it A? Is this in rotational equilibrium? A, yes. B, no. Is that in rotational equilibrium? A, yes, or B, no? We'll stop at 25. Okay, this is not in rotational equilibrium. Let me ask you another question, and I'll come back and answer this question. Is the 100-Newton force, does the 100-Newton force, does it provide a clockwise torque, or does the 100-Newton force provide a counterclockwise torque? Clockwise or counterclockwise? That is, this force, is that a clockwise or a counterclockwise torque? All right, I'll stop at 30 seconds. Yeah, that's right, D. Okay, so this provides a counterclockwise torque. I can imagine, I always like to hold my pencil here. If I pull down on a force on this side, it causes it to rotate in that direction. This is not in rotational equilibrium because the clockwise and the counterclockwise torques are not equal. In fact, which one is bigger, the clockwise or counterclockwise torques? The counterclockwise torques. So here, the counterclockwise torques are bigger than the clockwise torques. I can calculate counterclockwise torques. It's going to be 100 newtons. That's my force. Remember, torque is force perpendicular times R. 100 newtons times 2 meters, and that's bigger than 50 newtons times 1 meter. All right, 200 is bigger than 50 newton meters. All right. Let's do one more question just to sort of jog your memory a bit. When you attach muscles to bones, there are 2 points, right? There is the insertion point and the origin. And then there is also the origin. Which of these is attached to the bone that moves? The origin or the insertion point or the origin? Which of these is attached to the bone that moves? This is where your muscle's attached to the bone, right? The muscle attached to the bone at this point. Which of these is it that causes the bone to move? The insertion point or the origin? It's in your book too, by the way, or your notes or whatever. I'll stop at 40 seconds. Excellent. Y'all know this a lot better than me. I have to look at my notes. This is all sort of new to me, but it's really cool. Like, I'm very excited to learn about it. I know that y'all probably known about it for years, but it's Well, if you know, on the quiz, there was a lot of this stuff, I thought, right? Yeah. Huh? Okay. So, all right, let's continue on. So, we're going to talk about application of muscle tensions, section in your book. The application of muscle tension. Just a couple of definitions that we want to understand. And then we'll work through some problems where we apply these torques to our muscles in a couple of different scenarios. First of all, we said this, but remember when we had a string, if we're pulling it between two different people, that there's a tension in that string, and the tension in the middle, for example, is bigger, smaller, or the same than the tension at the point where the person is pulling. Bigger, smaller, or the same? It's the same. It's the same all the way throughout the entire string. And so that's true for muscles as well. The force of tension is the same throughout the muscle. So, for example, I'm going to draw it like a rope, but you can imagine it like a muscle, but I don't really know muscles that well. Say that I'm pulling on this end with 100 newtons. That's going to give me an equal and opposite force of 100 newtons. That's an application of which law, by the way? Let's do this as a clicker question. Is this the application of Newton's first law, second law, or third law? The fact that if you pull on a rope with 100 newtons, then you're going to get an equal and opposite force on the other end. Is that an application of Newton's first, second, or third law? You should have a good working knowledge of Newton's laws for the test. I know the definitions, Cole. All right, I'll stop at 30 seconds. Okay, that is an application of Newton's third law. Remember, Newton's third law says that if you have one force, that you're always going to have an equal and opposite force. Remember, this is also true even if you're not touching, right? Like if I'm hovering above the Earth is pulling down on me with 700 newtons of force, that's my weight, and then I'm doing what to the Earth? I'm pulling up. We're all pulling up on the surface of the Earth, right? You're all applying a force to the Earth just because of the mass that you have. Okay, now when we apply tension to our muscles, there are a couple of different contractions. Y'all probably know these definitions, but I'm going to write them nonetheless. I'll give y'all just a second. I'll go on from here. May I? So, no, what happened? There we go. So there are isotonic and isometric contractions. An isotonic contraction is when the contraction of your muscle causes the bone to do what? Somebody said it, what? To move, that's right. It's Jessica? No, Jessica? Really? Yeah. All right, so the contraction of the muscle causes the bone to move. All right? And an isometric contraction, on the other hand, it's a contraction of the muscle. You understand what my hash marks mean? Just repeating that. That contraction of the muscle does not cause the bone to move. All right, so if I'm in the gym and I'm lifting the 5-pound dumbbell, this is an iso what contraction? This is an isotonic contraction. But if you're like at the yoga class and you're doing this, that's a what? That's an isometric contraction. So it doesn't cause the bone to move. Isotonic and isometric contraction. Now there are several different types of movement. When you're talking about your bones, and I'll show you some pictures in just a second, there's a gliding movement. I feel like such an imposter because I just learned this. But y'all know there's a gliding movement, like where your bones glide with opposed to one another? Where is that? Oh, isn't it your jaw? Your wrist and your ankle. That's what I learned. There's a gliding movement. So this is when two flat bone surfaces glide across one another. There's an angular movement. Oh, so this is an example of this one, I'm sorry. An example of this one, of the gliding movement, is like the wrist and ankle. They both have bones that move, that glide across one another. An angular movement. This is when the angle between the movable and the immovable move. So a good example is you got your big old bicep that's causing your arm to move. I have my immovable bone here and my movable bone here, and the angle is changing. So you have a big angle, small angle, big angle, small angle. So that's an angular movement. The angle between the movable and immovable bones change. I think that's misspelled. I don't think there's an E there. I'll bring it up a little bit for y'all. What's the example on that? For example? Right. Yeah, so your arm, your legs also. There's some other examples. And then the third that the author gives in your book is the rotational movement. I understand there are some like subcategories among these, but I think these are the three large categories: gliding, angular, and rotational movement. Y'all think of anything that is rotational? Rotational movement. Right. Yeah. See, I was trying to give y'all a key. But what is your shoulder as well, right? You like in the Muppet movie. Y'all seen the Muppet movie? Where what's his name, Gonzo? He's doing the head bowling, right? That's rotational movement. You have something that rotates. You haven't seen that movie? It's like the best movie in the whole world. Okay, rotation. The bone twists on its long axis. All right. Let me show you a body. I mean a picture. I come away from this for just a second. Where is it? Oh, here we go. All right, so we have three different. This top part is the where you pivot, where your neck pivots back and forth. What type is this called? Rotational. This one, like in your arm, where you have a hinge. What is this called? The angular. And then in your hand, the bones glide back and forth across one another, and that's called, of course, the gliding movement, right? I think y'all probably know that, at least those of you that are athletic training majors. I know that there are some others, but y'all have seen this in your classes, right? If you're athletic training, at least. Okay. Very interesting. I might change my major, athletic training. How would that be? Oh, I should probably stay. Awesome. Yes. Awesome. Okay. Now remember we had those levers in the body? I want to try a quiz on this. So here I have some pictures of levers that are in the human body. Let's see, do you want the ones with the answers or no answers? Okay, no answers. So here, these are three different levers in the human body. And I want to know which class these are. So let's do this first one first. Is this A, class 1, B, class 2, or C, class 3? This is a guy applying a force. His leg, the weight acts as the load, and the pivot point, of course, is on the ball of his foot. So is that class 1, 2, or 3? All right, I'll stop at 28. 28. That's all good. That's class 2. Let's try this middle one now. So now we're looking at this one using the same options. This is a guy, your head pivots about a point that's sort of inside your neck. The weight is in front of that pivot point. So if this is my pivot point, more of my weight is at this point. We'll talk about center of mass soon. So it's a front of that pivot point. But then the force comes from the back of my neck. So what kind of lever is this? Class 1, 2, or 3? I'll stop at 45. That is correct. That's class 1. Now let's do this third one. If you've been paying attention, you should know what it is. But what is this third one? My pivot point is here at my elbow. My bicep attaches right about here to my forearm, but the most of the weight is out away from that attachment point. All right, I'll stop at 30 seconds. Excellent. So that's a class 3 lever, which is what, like what is class 3 like? Tweezers? Tweezers, yeah. How'd it go? It was scissors, wheelbarrow, tweezers, right? Class 1, 2, 3. Scissors, wheelbarrow, tweezers. Like sweet, SWT. Scissors, wheelbarrow, tweezers. Sweet. Sweet. Okay? Which of these is the most efficient lever? If you want to get a job done, which is going to require the least force? Class 1, 2, or 3? Oh, like if you want to move a load, which lever will require the least force? Just click it in. What do you think? So that's not a very good question. It's going to be usually class 1, but it can be class 2, I think. I'll have to think about it. Yeah, they both have a Yeah, so just I'm not going to click a right answer on that. I'm just going to stop it. Okay, but make sure you click in because you will get credit. Okay? All right. All right. Let's move on. Let's work a problem. You have a similar problem in your book, but I'm going to work a couple of problems regarding your bicep. If you have big old biceps like me, no. I should come in with like a balloon in my shirt one day. I'm not really that strong. But, so let's say that you have an arm. All right. Inside the arm, you have your bones. And then in that, you have muscles that are attached. You have a muscle that is attached right about there. Now let's mark some distances. First of all, I want to figure out what is the force in the bicep. I have a certain force. I'm going to call it FB. I want to figure out what is that force in the bicep in order to hold a mass out here. I'm going to say that this mass is, I don't know, 5 kilograms. Like more than 10 pounds, 10 or 15 pounds. All right, so I have a 5 kilogram mass, and I want to know how much force is required by the bicep to actually hold it at a 90-degree angle like that. Difficult or easy? It's easy? Well, let's see. Let's just see. So I need to label some distances. So this is a torques problem. My axis of rotation is right here. And then I have a couple of moment arms. Remember, the moment arm is the distance from the axis of rotation to where the force is applied. How many forces do I have here? It looks like 2, right? But there are actually 3. So let me label the 2 that you're thinking. I have a force FB that I've already labeled. I also have a force here, which is the weight of this block, which is going to be M times G. That's going to be 5 kilograms times 10 meters per second squared, or 50 newtons. All right, so I have that force. There's a third force. What is it? No, not the normal force. The weight of the arm, right. So the weight of the arm, just even if I'm not holding any mass at all, the bicep is required to put some sort of force on the arm in order to hold it in place. So I also have the weight of the arm. So I don't know how much your arm weighs, a couple kilograms probably. So we're going to say 2 kilograms times 10 meters per second squared, and that's going to be 20 newtons. Now let's see, my arm is about 40 centimeters from elbow to hand. So this distance from here to here is 40 centimeters. Let's say that this distance is 20 centimeters, and I don't know exactly the distance that the bicep is attached to the forearm, but it's just a few centimeters. So to make it easy, I'm going to say 5 centimeters, just a rough estimate. All right? And so this distance from here to here, I'll call that 5 centimeters. All right? I want to know how much force is required by the bicep to put this in rotational equilibrium. What is FB? For rotational equilibrium. By the way, would this be an isotonic or isometric contraction? Isometric, yes. It's an isometric. It does not cause the bone to move. So I'll just label that over here. Since we're still trying to learn these definitions, this is an isometric. All right, isometric. All right, so what is FB for rotational equilibrium? All right, what we want to do here, we know that for rotational equilibrium, that the counterclockwise torques have to equal the clockwise torques. All right, which of these are providing clockwise torques? Which forces, or which force are forces? The weight. That's right. So here, if I imagine this rotating in this direction, if I pull down, that makes it go clockwise. So this force and this force are causing the arm to move in the clockwise direction if the force of the bicep wasn't there. So this is going to equal our 20 newtons times our moment arm, which is 20 centimeters. I'm going to go ahead and convert this to meters. Now, on the test, I won't expect you to convert units, but I'm going to convert it to meters, 0.2 meters. That's just 20 centimeters, plus 50 newtons times 0.4 meters. All right, so I know that that has to equal the counterclockwise torque, which is going to be the force of the bicep times 0.05 meters. Y'all can solve that if I gave it to you? Okay, it's easy. How many math problems? You know, a few. 2 to 12. No, just a few. No, you'll definitely have a torque equilibrium problem. All right. You'll have some calculation problems regarding Newton's second law. I think we might have had one on the quiz similar to that. Is that right? We had one on the quiz? Simple algebra. Well, let me show you. So I want to get FB all by itself. In order to do that, I want to divide both sides by 0.05. So I'll divide this side by 0.05 and this side by 0.05. And when I do that, that cancels out here and here, and then I get an expression for FB. Right? 20 times 0.2, that's equal to 4, plus 50 times 0.4, 20, divided by 0.05. I know what that is right off. What is it? 480, that sounds right. So 480 newtons is the answer. Look, this is the force required just to hold a 5 kilogram mass. A 50 newton force requires an order of magnitude bigger force by your bicep. So it requires really large forces in order to hold smallish masses in our hand. 480 newtons. All right. I made an assumption here. Anybody catch what the assumption was? I don't think I said this, but what is it about the force as it's applied to the forearm that I've assumed here regarding our torque calculation? That what? No. I mean, that's true that the force due to the bicep is larger, and we found that to be the case. But that wasn't my initial assumption. Remember, torque is equal to F times R. Right? Which is what I've said here. But there's something special about that force, and what is that? We had a little symbol, an additional symbol. The perpendicular, right. So I've made that assumption here that the force due to the bicep was perpendicular, which is pretty much the case, right? That if I hold my arm like this, my bicep is pretty darn close to 90 degrees from my forearm. But if I hold it out like this, well, how's my bicep? Is it more or less than 90 degrees? It's more. Now, how is that going to affect the force that the bicep is required to exert to hold the same mass up? Huh? I mean, you've probably experienced this, right? Is it easier or more difficult to hold something out like this than it is right here? It's what? It's more difficult, right? It's a lot more difficult to hold a mass out like this because of this reason that if I push it out, I have my bicep pulling up in this direction and also pulling up in this direction. It's only this force that's actually causing the torque. It's only the perpendicular force that causes the torque. Right? So if I hold my arm out like this, it's only a portion of that force that's causing equilibrium. Go with me on this? Let's try a torque problem with your clickers, okay? Give me a moment. And we had a similar one, but I'm going to let y'all try it on your own. I'm going to draw it a little more simply, but it's the same scenario, just so y'all can try it. Here I have an arm. It pivots at the elbow. I have several forces on it. I have this force, and I have this force. I'll call this F1, F2, and F3. I'll call this distance, these aren't reasonable arm distances, but just to make the numbers easy, I'll call that 1 meter, this 3 meters, and this 6 meters. If F2 equals 5 newtons, and F3 equals 10 newtons, excuse me, let's draw F3 down, I'm sorry. No, let's keep it that way. Sorry, I'm changing this a little bit. I want to know what F2 is. And let's say that F1 is 1 newton. All right, I want to know what F2 is. Okay, y'all go and start working that out. I'm going to blank the screen in just a second as soon as you get those numbers written down. And I'll put the options up for you. All right, I'm going to blank it for just a second. All right, here are your options. Try it out. I just want to know what F2 is. I'll have something similar on the test next week. There are also some problems in your book that are similar to this, examples that they work out. In this, you want to set your clockwise equal to your counterclockwise torques. Doesn't really matter which is clockwise and which is counterclockwise. You just want to set one torque in one direction equal to the other torque in the other direction, recognizing that sometimes you'll have multiple torques or multiple forces that provide torque in one direction. In about 10 more seconds, I'll stop at 2:30. Excellent. B is the right answer. You're doing really well on these. Your test questions are going to be similar to this. So if you're doing well on these questions, then you should be pretty good for the test. I recommend that you study nonetheless. But if you're not, then come see me or read the book more closely, or just I can help you if you come see me. All right. So here I have two torques. These two torques are providing a what is that? A counterclockwise torque. Though as I said, it doesn't really matter if it's clockwise or counterclockwise. You're just setting them equal to one another. So get rid of this. I have some space. I have F1 times 1 meter plus F3 times 10 meters. And this has to equal F2 times 3 meters. I'll put in some numbers there. Yeah, Destiny? Oh, yes, you're right. Thank you. Plus F3 was 10 newtons. That's 6 meters. And that's equal to F2 at 3 meters. Right. This is, if I add this up, it's going to equal 61. The units for torque are Newton meters. If I have to divide both sides by 3, so my 3's canceled there, and then I get F2. 61 divided by 3 is 20.3 or so, but I'll just call that 20 newtons. Turned out that 1 Newton force hardly provided any torque at all, so it's as if it wasn't even there. So F2 is 20 newtons. If you're having trouble with the algebra on that, please come see me. I can help you. Let's work another problem. You have a similar one in your book. And so, as I said, this is the best case scenario where your arm is perpendicular, or the muscle is applying a force perpendicular to the arm. But one of the worst case scenarios is, as I said, like when your arm is out like this, and then it requires a very large force. And we have a problem with the deltoid muscle, which is in your book, but I'm just going to work it here. Let's see, I think this is it. All right, so this is a picture of the muscle, the deltoid. Where is it? Right here? Is this it? Oh, yeah, that's it right there. So the deltoid muscle, which allows you to lift your arm like this, right? And if you do that, you can sort of feel it contracting. Isotonic or isometric? That's right, isotonic. Isn't that right? Yeah, okay, good. All right, so I want to know what is the force here. Hold on, I want to see how your book does this. Just give me just a moment. Okay. We're not going to do a lot of trig in this class. In fact, I'm not going to expect you to know any trig at all because that's not a prerequisite for this course. But I do want to show you just sort of the math, how this will work out. And it does it in your book as well. But your calculations on the test will be much simpler like the one that we did previously. If we look at our torque, it's equal to FR. But actually, there's another term there where it's FR times the sine of the angle theta. All right. Don't worry about what that means, but basically it's saying that I want the perpendicular force. So if I multiply F times sine theta, that gives me the force that's perpendicular. So you see, if I'm applying a force to my shoulder, my arm, or whatever, if I apply it like this, then that force is entirely perpendicular, correct? And in fact, my angle is 90 degrees. Anybody know what the sine of 90 is? It's equal to 1, right? So then that force is all perpendicular. However, if I apply the force at an angle, then not all of the force is perpendicular. I have what we call a component of the force that's in that direction, and then I also have another component of the force that's in that direction. So I have forces that are pulling up and forces that are pulling to the side. Y'all with me on this? Yeah. So when you're applying a force on your arm that's at a steep angle like we have here, then a lot of that force is not going perpendicular. Instead, most of that force is going in this direction, which doesn't provide any torque at all. Remember, it's like the door. Did y'all try that when you were out? You remember what I said? Like where you don't push the door perpendicular, but instead you push it parallel to the door, and nothing happens, right? If you tried it, you figured it out. Who tried it? Nobody? All right. So anyway, if you're at a really shallow angle like this, where this angle theta is really small, then you're going to require a very large force. So let's just see this. Um, we'll do it in pounds and inches. Your book says that the weight of the arm is about 8 pounds, right? And let's see, this distance right here is roughly 6 inches. So we're going to calculate the torque now. Instead of in Newton meters, we're going to calculate it in inch pounds. All right, and this distance, the distance from your shoulder to your forearm or to your elbow, is about 10 inches. All right, so I have two torques. This will be torque 1, and the torque that's applied here will be torque 2. I know that torque 1 has to equal torque 2 in order to have equilibrium like this. And so my torque 1 is going to equal the weight of the arm, that's 8 pounds, times 10 inches. And torque 1, or excuse me, this was torque 1 right here. This is torque 2. Torque 2 then is going to be the force due to the deltoid muscle. That's the force being applied by the deltoid muscle, times 6 inches, times the sine of that angle, 10 degrees. As I said, don't sweat the math here very much because you're not going to see any trigonometric functions. That's what that sine is. But I just want to show you what that force is. So I have 8 times 10, that's 80, divided by 6, and then divided by the sine of 10 degrees. And so that gives me a force on my deltoid of 80 pounds. Right? A force on my deltoid just to hold my arm up of 80 pounds. That's pretty cool, right? I mean, that's a pretty big force, 80 pounds. That's like my boy, he's 9. He's 80 pounds. And so that whole force is required just to hold your arm up. And the reason is because it's applied at such a steep angle like this. All right? Y'all follow me on that? Well, you would say 8 pounds times 10 inches divided by 6 inches times sine of 10. But don't worry about it because you're not going to have to do that on the quiz or ever again in your entire life, probably. Okay? Still with me? All right. So how this might crop up on the test is I could ask you, for example, if I have an object that's like this, and I have several different forces that are applied, say I have F1, F2, and F3, something like this, I would ask if the forces all have the same magnitude, which force provides the most torque? All right, let's try that out. Which force provides the most torque? Is it A, F1, B, F2, or C, F3? Which force provides the most torque? F1, F2, or F3? Which force provides the most torque? They're all the same force. They all have the same magnitude. Which force provides the most torque? All right, I'll stop at 48. 48. Okay, excellent. F3 provides the most torque because all of F3 is perpendicular to the axis. Right? So F1, for example, it has a portion of its force that goes in this direction, which provides no torque at all, and then a portion of it goes in that direction. And it's only the perpendicular part, that perpendicular component, as we call it, that provides the torque. Y'all look really excited about this. Are y'all excited? Okay. Okay, this comes up also, and your book goes into a lengthy discussion, about this with the, that's what's the muscle called? The erector spinae. Spina? How do you say that? Spinae, excuse me. And so this shows why when you bend over, as this guy is doing, he sort of looks like me, I think. Don't you think? All right, when this guy bends over, he has the weight of his arms and then whatever thing he's supposed to lift, and then he picks it up like this. You're not supposed to do it like that, right? How are you supposed to lift things? Right, you're supposed to bend your knees like this and then pick it up and then use your legs, keeping your back straight, right? That's why they make those belts for people when they lift heavy things and stuff like that. The reason is because you have this force that's being exerted onto your spine or by the muscles in your back. And see, they're at such a shallow angle there that they require very large forces to cause rotation in that direction. To cause rotation from here to here, because of this small angle, most of the force isn't causing the rotation, isn't going up. Instead, most of the force is going in this direction. So if I were to divide this force that's being provided by this muscle, what's it called? Spinae, the erector spinae. Most of the force, some of the force is going in that direction, but most of the force is going in that direction. And this force provides no torque at all. All right, so that means that force provided by that muscle has to be really large, which isn't good for your back muscles. Okay? Now follow me on this with me? Okay. Your book goes into a little bit more discussion on this. It's certainly worth reading, but that's the gist of it. All right. The final section in this chapter has a lot of information in it, by the way. As I told you, this is basically the first third or more of a whole year course in our Physics 101, 201 courses. Is on center of mass and balance. They talk about how when you're balanced, your center of mass is right about here in your belly button, sort of in between your back and your belly button, inside of here. Your center of mass is the center of mass, or it's sometimes called, as it is in the book, the center of gravity. It's a point where you can imagine all of the mass is located. Right? So for example, like I said, about your belly button, in between your spine and your belly button. On a meter stick, where is the center of mass? This is a lot simpler object than the human body. Where's the center of mass on a meter stick, which is 100 centimeters long? At the 50 centimeter mark, right? If it's symmetrical, which this one is, it's at 50 centimeters. There's a cool little thing that y'all can do. And like if you're out and about with your friends and you have a meter stick, you can show them this, okay? You can take your fingers and do it like this. And as you just pull your fingers into one another and see how this one's moving, but I'm going to tell you that the fingers are eventually going to meet at the center of mass. You believe me? You don't believe me, Jessica? Seriously? All right, watch. Oh, now this one's moving. Oh, now that one's moving. Oh, oh, oh. Can you tell me where it is? It's at 50. Oh, and the crowd goes wild. But look, I'm going to amaze you again because this is really cool. The reason for this, by the way, is if we think about friction, remember friction was proportional to just this coefficient of friction, but also some force. What was that force? The normal force, right. So as we come in, that normal force is changing until I get to the very center. And at one side, the normal force will be less than on the other side, and so I'll get less friction, and then that'll be the finger that moves, and then this is the finger that moves until I get to the center of mass at 50 centimeters, right in the middle. That's pretty cool, right? Like your friends, they would be really impressed if they saw that. But it gets more amazing, because if you take a piece of lead or some other bendable weight, like if you have it in your pocket, you happen to, and you can put it on the end, where do you think the center of mass is now? Is it at 50 centimeters? To the left of 50 centimeters? That is over here, or to the right of 50 centimeters, over here? It's to the right, right. So it's no longer here. In fact, if I let this go, it'll fly off because my center of mass is somewhere else. So watch this. I'm going to do this. You think it'll work this time? No. Well, you are hard. Look, it's moving. Oh, now this one's moving. And now it's at the center of mass, roughly. Okay? That's really cool, right? It's just because of the friction, the way the friction and the normal force, so they sort of interplay until your fingers reach the same spot. All right. So for example, with a meter stick, the center of mass is at 50 centimeters. If I have a meter stick that's weighted on one end, like over here, like if I put lead weight, then for example, the center of mass would be at, I think it was wound up to be like 20 centimeters or something less, right? It's where all the mass is located. Or you can imagine if you could take all the mass and condense it down to a single point, that it would all be at that place. All right. And then, so this comes up because you want to balance so that your center of mass is right over your feet. So if this is me, I want this to be exactly like this because that requires the least force from the muscles on my body. Right? If I have that, if I leave it, it's going to be somewhat stable. Whereas if I bring it off like this, then I have to have very large forces acting on my spine or on my back in order to keep it upright. And they talk about how if you hold a large object like this, what do you have to do when you pick up a large object? You have to bend back, right? So you have to bend back. That's to change your center of mass, because when I have this large object, whatever it may be, so this is me, my center of mass is normally right here, but this is me holding a very large object. Now my center of mass is somewhere like right here. And now I want to bend backwards so that that center of mass is right over my feet, right over my feet. Okay? You with me on this? Okay. I think that's all for chapter 1. We are going to move on to chapter 2. I'll have to send y'all an email later about what we're going to do about the quiz and stuff. We have another day. So just go ahead and be reading chapter 2. I'm uncertain now. What's today? Tuesday? Today's Thursday? It's Tuesday. All right, let me ask y'all what y'all want. So I'm going to give you some options. This is just regarding the quiz and the test. So first option is we will have the test on Thursday. R stands for Thursday. And the test will cover chapter 1. The second option is that we will have a quiz on Tuesday for part of chapter 2. Test on Thursday for 1 and part of chapter 2. All right? Or we could do a quiz on Tuesday for part of chapter 2. And again, this helps you because the more quizzes we have, that means the more that we're going to drop in the end. So if I split up chapter 2 into 2 quizzes, which is what I would do, then that's going to be an extra quiz in the end. I can't guarantee that we're going to have 6 or more quizzes. We'll have at least 5. No, I say 5 quizzes. We'll have at least 1 drop. But if we have more than that, then I'm okay with that. So we have the quiz on Tuesday and then the test on Thursday. with just chapter 1, all right, which is a lot of material in itself. This is non-binding to me, but I want to know what you feel. It's still my decision in the end. That's what I'm saying. Yeah, next week, not this week. Test on Thursday, chapter 1. Only, no quizzes. Quiz on Tuesday, chapter 2, part of chapter 2. Test on Thursday, chapters 1 and 2. Or quiz on Tuesday, test on Thursday, but only chapter 1. All right? You have your opinion in? All right, so a few more seconds. We'll stop at 1:52. I have to look at these in private, sorry. You want to have all of chapter 2 on the test next week? That wasn't even an option. I don't know how you got that in there. No, let's see. Quiz on Tuesday. Okay, we can do that. So we'll have the quiz on Tuesday, chapter 2, and then the test on Thursday would just be chapter 1. Is that clear? Okay. All right, so on Tuesday we'll have a reading quiz. It'll be the last 20 minutes of class. It'll be on a portion, no, it'll be on chapter. I'll let y'all know. I said part, didn't I? Yeah, it'll be a part of chapter 2, just like the physics portion of chapter 2, and which we should be covered by then. All right? And then the test will be chapter 1. All right? This isn't a democracy. I don't want to give y'all that. I was just getting your input, okay? But that was there are only a few people that didn't want those options. Okay. Well, let's move on to chapter 2. Chapter 2 is all about fluids. It's kind of cool. We're going to look at pressure and the flow of fluids. We'll look at stress and strain in solids and how that applies to bones, for example. Later in the chapter, we'll deal with like delivery methods, delivering medicines and what have you, measuring blood pressure, measuring pressures such as that. It's a fairly interesting chapter. A lot of it you've probably seen before in some of your other classes, but a lot of it's probably new as well. All right. Chapter 2 is on pressure. Or the first part of chapter 2 is about pressure. We're going to define pressure first of all. Your book uses a lowercase p for pressure, but it's force per unit area, or F over A. That is a force per unit area. Anytime you want to move a fluid, it requires pressure. Like if I'm moving a solid, I just talk about forces, right? But if I'm moving a fluid, I have to imagine a pressure because, like if I move my finger back and forth to fan me, does that really fan me much? No, actually, because of the way the fluid acts, where it moves around my finger back and forth, this doesn't really do anything to fan me. Like if I'm hot or whatever, oh, man. Right, I have to imagine the force, that is the force that the book is applying onto the air around it, the fluid, and also the area of the book. So if I want to move more fluid, I do what? I get a bigger area and also apply a bigger force. So I have to consider both of those, the force for the area. So whenever I want to move a fluid, which, by the way, a fluid includes both liquids and gases. So a fluid is anything that flows. All right, so whenever I want to move a fluid, I have to consider pressure, not force. not just force. Right, because of the nature of the fluids, that they flow. They'll flow around whatever it is that you're trying to apply the force with. All right? This comes up a lot. Can y'all imagine some places where we want to move fluids? Where are some places we want to move fluids, like in your area? And what is that, Jessica? Okay, in the heart, right. So the heart, we'll talk about the heart, how the heart, okay? Okay. The heart will apply pressure to the blood, and that pressure goes all throughout the body. That's your blood pressure. Oh, what else? Where do you want to move fluids? Okay, your lungs, right? That's just what I was thinking. So your lungs, by changing the volume of your chest cavity, you can change the pressure in your chest cavity, in your lungs, and we'll talk about that with regards to the ideal gas law. What are some other ways you want to move fluid? Kidneys? Okay, yeah. Okay, yeah. Kidneys move fluid. Anything else? I said delivering medicine with IVs and stuff like that. If you want to deliver medicine with syringes, yeah. So there are lots of places where this becomes relevant in moving fluids. There are a lot of different units for pressure, and they're all a measure of force per area in some way. So the SI unit is the Pascal. In the SI system, it is the Pascal, which is abbreviated PA. And 1 Pascal, I usually put a base on my P, so that's a P, is equal to 1 Newton per square meter. That's a force per unit area. A square meter, meters times meters, gives us area. So that's the SI unit, but that's actually not used very commonly, at least in your field. Yeah, PSI, which is the British unit. PSI. What is PSI? Right, pounds per square inch. So like, for example, we measure the pressure in our tires in PSI. We run about 30 to 35 PSI or so. You'll also see in the medical field millimeters of mercury. This is millimeters of mercury. It describes the height of a column of mercury, and we'll talk about how you get that, like with a barometer, or what that means, how that translates into a pressure. That'll come up pretty early on. Millimeters of mercury. Similarly, sort of in the same category as this, you can also have inches of mercury. So just measuring the height of that column of mercury, instead of measuring in millimeters, you can measure it in inches. You can also have centimeters of H2O. So again, all of these are measuring the height of a column. It's measuring the height of this column. And it's either measuring in millimeters, inches, or centimeters. And inside the column is either mercury or what? Or water, right. So this is going to be centimeters of water. And we'll see that. Atmospheres. Is a really common measurement of pressure. 1 atmosphere is equal to 100,000 newtons per square meter, or pascals. And this is the pressure due to the atmosphere above you. And we'll talk about that as well. If you're a diver also, I'm pretty sure any divers in the class? I mean, you talk about pressure and atmospheres. as you go underwater. Let's see, I think that's about it. I don't know, there's also the bar. I don't know where the bar is used exactly. Does anybody know? I think this might be used in like atmospheric pressures. Is that right? You ever heard this? No. Okay, anyway, the bar is a measurement, and it is equivalent to 100,000 pascals. Okay, this is just one atmosphere. Yeah, so it's also equivalent to one atmosphere. All right, so there are lots of different measurements for pressure, and we'll talk about these and how we get these, especially these category here, where you're actually measuring the column of something and converting that into a pressure. All right. Okay, now there are three possible sources of pressure in a fluid. Three possible sources of pressure. We'll probably get through the first one before class is over. Three possible sources of pressure in a fluid. Oh, let me show you something actually before we move on to that, because this was kind of cool. All right, so three possible sources of pressure in a fluid. And the first of these is the weight of the fluid. The second is the external force applied to the fluid. So like in that clip, it was the weight of the fluid that provided the pressure on the floor. The second scenario is an external force that's actually applied to the fluid. So for example, like in a syringe, you apply a force to the end of the syringe, and that applies a force to the liquid, which causes a pressure within that fluid. And then the third thing is just internal forces due to molecular interactions. Molecular interactions. And when we get into this, that'll be the ideal gas law, describing the interplay between pressure and volume. I'm just going to write the ideal gas law here. PV equals nRT. You probably had that in high school. If not, we're just going to deal with it very briefly. All right, so three possible sources of pressure. Let's look at the weight of a fluid. What time do we have? And we have a couple more minutes. So the first is the weight of a fluid. Imagine that you have this container of water or whatever. All right? And I have a point that's down within that container of water. And I'm actually going to describe this as a cube. So I have a cube down within that container of water. And I want to know what is the pressure right here. I know that pressure is equal to force over area. Now, the only part of the liquid that is causing a pressure at this point on my cube is this column of liquid that comes up on top of it. Like the fluid over here has no impact at all on the pressure at this point, because the weight of the fluid is all pointing downward. And so the pressure is all due to that column. So I can imagine this column of fluid. It can be water. It can be air too, right? We're all walking around. As you leave today, imagine that you're walking around with this column of air that goes up above you many, many kilometers into the atmosphere. Okay, and the weight of that is all pushing down on your head with actually quite a large force, like, I don't know, 10,000 newtons or so, roughly, on top of your head. Did you know that? Yeah, so you have this immense force that's pushing down upon you just due to the atmosphere. All right, so I have this column of liquid, and I can figure out what is that pressure. That pressure is force over area. The weight of that pressure is the mass of the column of water times gravity divided by area. Now, I'm not going to go through the derivation, but we can get to this expression based on this, which says that the pressure is equal to the density of the fluid times the acceleration due to gravity times h. So if I take this mass over area, it gives me density times height. Don't worry about how we get to that step. This is what we're worried about right now. All right, so my pressure at some point in the depth of a fluid of water is equal to rho times g times h, where rho is the density. Remember, density is a mass per unit volume. You sort of need to know that in just sort of passing. G is my acceleration due to gravity, which is 10 meters per second squared. And then h is the depth. Right, so if I have a really dense liquid, if I'm in a dense liquid, I'm going to have a much larger pressure down at a certain height. Or if I'm deeper within a liquid, I'm going to have a larger pressure. Okay? We'll stop there. We'll pick back up with this. There will be a quiz on Tuesday. It will be a portion of Chapter 2. I'll let you know, like the page numbers, on Thursday. And then the test will be next Thursday, and it will just be Chapter 1. I think that's probably a wise decision for y'all.